Hello everyone, welcome to my presentation. My name is Vipin Kumar Kukala and I'm a PhD student at Colorado State University. Today, I will be presenting our paper titled INDRA, which stands for Intrusion Detection using Recurrent Autoencoders in Automotive Embedded Systems. The co-authors in this paper are Surya Vignesh Thiraloga and Dr. Sudeep Pasricha. I would like to begin this talk by giving a brief introduction to automotive systems and motivation for our work. Then I will be discussing some of the prior works in this area and discuss our proposed work in detail with experimental results. Modern-day cars consist of various processing elements called ECUs or electronic control units, such as engine control unit, transmission control unit. These ECUs run various time-critical applications that have strict deadline constraints. And these ECUs are distributed across the vehicle and communicate with each other using the in-vehicle networks. CAN and FlexRay are some of the example in-vehicle network protocols. The figure here on the right shows an example in-vehicle network architecture of a real-world vehicle. We can see that there are multiple in-vehicle networks connecting different ECUs through common gateways. Looking at some of the trends in automotive systems, we can see that the figure on the top right shows the increasing number of ECUs over time. And the figures on the bottom left and right shows the increasing software complexity and data rates. This resulted in increasing the overall system complexity of automotive systems, which resulted in three major problems in reliability, security, and real-time performance. However, security in automotive systems will be the main focus of today's presentation. Why security? We can see that modern-day cars are becoming increasingly connected with the various external systems, which makes them vulnerable to various security attacks. Thus, security is an increasingly crucial requirement in automotive systems. The first full vehicle hack was demonstrated in 2010 by Kosher et al. In 2015, the attackers were able to hack into a Jeep remotely and gain access to the vehicle. And we've seen several other cases where automotive systems were subjected to attacks. The most common thing between these attacks is all of these attacks are launched by gaining access to the in-vehicle network. Hence, network security is a major concern in automotive systems, and especially in connected and autonomous vehicles. ECUs in automotive systems communicate with each other by exchanging messages using in-vehicle network. These messages are periodic in nature for safety-critical systems. The figure on the bottom right shows an example in-vehicle network data of a real-world vehicle. This is the complex time series data with various dependencies. Also, automotive attacks achieve their goal by actually modifying the content of these messages. Thus, an intrusion detection system, or an IDS, often acts as a last line of defense against these attacks. Traditionally, firewalls and rule-based systems are used to detect intrusions, which are not effective as they fail to capture the complex patterns in time series data. A more promising solution is using deep learning to detect intrusions. The large availability of data and the ability of deep neural networks to detect the complex patterns in time series data made them a promising solution. However, traditional feed-forward neural networks cannot be directly employed to detect intrusions as they are not efficient in capturing the complex time series data dependencies. Thus, a new type of neural networks called sequence models can be used when working with sequences or time series data. Recurrent neural networks, or RNNs, are the first type of sequence models that allows information from previous outputs to be fed as input to the current state. The figure on the bottom left shows a simple RNN network. When expanded, an RNN network looks as follows. RNNs are widely used in natural language processing and machine translation applications. However, RNNs lack the ability to learn long-term dependencies in the sequences. The second type of sequence model is called long short-term memory network, or also known as LSTMs. Similar to RNN, LSTM uses chain-like repeating modules. LSTMs uses an additional state called cell state and 3 different gates to learn long-term dependencies in sequences. The third type of sequence model is gated recurrent unit, or also known as GRU. GRUs combine the hidden state and self-state information in the LSTM to one state. They also use 2 gates as opposed to 3 in LSTMs. Moreover, GRUs are relatively new and have high potential. In this work, we use GRUs due to their ability to have long-term memory and low computation and memory overhead. The last type of special neural network is autoencoder. An autoencoder is used to learn the sparse representation of the input data in an unsupervised manner. An autoencoder has 3 parts: an encoder, an embedding, which is a sparse representation of the input data, and a decoder. Autoencoders tries to learn the sparse representation by trying to recreate the input at the encoder at the output of the decoder and try to minimize the reconstruction loss. Autoencoders are mainly used in dimensionality reduction and information retrieval. In this work, we integrate GRUs with autoencoders in an unsupervised learning setting. Looking into some of the state-of-the-art automotive intrusion detection works, in 2016, Taylor et al. Proposed a LSTM-based model that can predict the message value at the next time step at a bit level. This prediction is compared to the real value to detect for intrusions. This approach fails to detect attacks when the early stage of attack interval is missed. Moreover, there's high computational cost associated with these techniques. In 2018, Weber et al. Proposed a RNN-based model to learn the normal system behavior by increasing the input data dimensionality and observing for deviations at runtime. This approach fails to detect small variations in attacks. In 2019, Hanselman et al. Proposed a multi-stage LSTM model to detect anomalies by learning the normal system behavior at design time. However, this approach suffers from scalability issues and has high computational overhead. Moreover, none of these techniques provide a holistic system-level solution which is lightweight, scalable, and reliable to detect multiple attacks. In order to address the earlier mentioned issues, we propose a novel intrusion detection framework called INDRA to detect intrusions in automotive systems. INDRA uses GRU-based recurrent autoencoder model to learn the latent representation of normal system behavior at design time. At runtime, INDRA uses our proposed intrusion score metric to quantify the deviation from the normal system behavior, which is used to detect the intrusions. We presented an analysis towards the selection of thresholds for the intrusion score metric. We compared our INDRA with state-of-the-art prior work, which were discussed earlier. Moreover, we implemented INDRA on a real hardware and performed an extensive scalability analysis. Looking at a high-level system model, we consider a scenario where multiple ECUs are connected using CAN bus. We adapt a distributed intrusion detection approach where each ECU monitors only the messages it receives. This results in having the real-time and intrusion detection applications being collocated on the same ECU. Moreover, we assume that the attacker can gain access to the in-vehicle network using the most common attack vectors, such as infotainment systems and OBD2 ports. For the communication model, we consider controller area network, or also known as CAN, which is the most widely used in-vehicle network protocol. The figure here shows the frame format of a CAN message. The arbitration field consists of the message ID, and the actual data that needs to be transmitted is in the payload segment, while the CRC performs error checking. It is important to note that the data or the payload segment of a CAN message consists of multiple signal values, which corresponds to different physical measurements or control values. An example CAN message with 5 different signals is shown here. In this work, we focus on monitoring signal level variation to detect intrusions. In the attack model, we've studied different types of attacks. These attacks are illustrated using the figure on the right. This figure represents the signal value corresponding to battery current from a real-world vehicle, and the shaded portion represents the attack interval. In the first attack, which is known as the plateau attack, where the attacker overrides the signal to a constant value over a period of time. In the second attack, which is the continuous attack, the attacker slowly overwrites the signal value to achieve a specific target value. The third is the playback attack, where the attacker uses a valid transmission from the past and replays it, trying to trick the intrusion detection system from not being triggered. The fourth attack is the suppress attack, where the attacker completely or partially stops message transmission from an ECU. The last attack is the flooding or DDoS attack, where the attacker floods the bus with messages so that the bus utilization goes up, making the bus unusable. In this work, we evaluate our proposed INDRA framework under each of these attack scenarios. In this slide, I'll be presenting an overview of our proposed INDRA framework. Our proposed INDRA framework has two phases, a design time phase and a runtime phase. Design time phase mainly involves training the model. It begins by acquiring the CAN bus data and pre-processing, which is then used to train the model. Once the model is trained, it is used for inferencing during runtime, where real-time CAN messages are given as the input and attacks were injected. The detection step computes the intrusion score and raises an intrusion flag in the case of the presence of an attacker. During the design time phase of training step, we use the model shown here to learn the normal system behavior. The model takes the input and passes it to a linear layer, which is connected to a GRU-based encoder. The encoder produces an embedding known as CV or context vector, which is then passed to a GRU-based decoder and a linear layer to recreate the input. Before training, we pre-process the CAN data by scaling the signal values from 0 to 1. We use a rolling window approach, where a window of fixed size is rolled to the right for every time step in the process of training. The model attempts to recreate the input at the output end, and with the goal of minimizing the reconstruction loss. We employ a mini batch training process to speed up the training. Moreover, the model uses backpropagation through time to update the weights and biases of the network. Once the model is trained during the design time phase, it is used to detect intrusions in the inference step. We inject multiple attacks to test the efficiency of our proposed intrusion detection system. We measure the deviation from the normal system behavior at two different levels. First is the signal level intrusion score, which is the squared error of predicted signal and the true signal. The second is the message level intrusion score, which is the maximum signal level intrusion score of all the signals belonging to that particular message. In this slide, a snapshot of INDRA detection during a plateau attack is shown. The figure on the left shows 3 signal values in a message, and the shaded region represents the attack interval. The input signal here refers to the value received at the ECU, and the predicted signal refers to the value predicted by our model. The figure on the right shows different intrusion score values for different signals and the intrusion threshold, which is used to flag the signal either anomalous or not. We can see that signal 3 was subjected to a plateau attack, and the intrusion score value of signal 3 stays above the threshold during the entire duration of the attack interval. In order to evaluate the effectiveness of our proposed INDRA framework, we conducted the following experiments. Firstly, we conducted sensitivity analysis for the selection of intrusion threshold. Secondly, we performed model exploration, where we compared INDRA with 2 other variants. The first variant is INDRA LED, which is similar to INDRA but without the linear layer after the GRU-based decoder. The next variant is INDRA LD, where the GRU-based decoder is replaced with a linear layer. We conducted this experiment to study the importance of each layers in the model. Next, we compared our proposed INDRA with 3 other prior works in this area. We performed an extensive scalability analysis to show the effectiveness of our proposed approach. We used detection accuracy and false alarm rate as the comparison metrics for all of our simulations. And we used the SynCan dataset that was developed by Robert Bosch and ETAS. All of our deep learning models are implemented using PyTorch 1.4 with CUDA 10.1 support. Our simulations are run on an AMD Ryzen 9 3900X server with NVIDIA RTX 2080 Ti GPU. We split the training data into 85% for training and 15% for validation. We trained the model for 500 epochs with a subsequent length of 20 and a batch size of 128. We've implemented early stopping mechanism with the patience of 10 epochs. We used the learning rate as 10 to the power minus 4 and used tanh activations for all the layers. We've used Atom Optimizer and mean square error as the loss function. This slide shows the experimental results of sensitivity analysis involved in selection of intrusion threshold. The figure on the left shows the accuracy versus validation loss of the final model for various attacks. The figure on the right shows the false positive rate versus validation loss of the final model for various attacks. We can see that after the 99.9 percentile of the validation loss, the accuracy starts dropping down and the false positive rates keeps increasing. We chose the 99.9 percentile of validation loss as the intrusion threshold. This is mainly because choosing a higher validation loss could result in not detecting the attacks that produce small variations. In this slide, we present the model exploration results of INDRA and its variants using two different comparison metrics. The figure on the left shows the accuracy of INDRA and its variants under different attack scenarios. The figure on the right shows the false positive rate of INDRA and its variants under different attack scenarios. We can see that INDRA outperforms the other two variants in both detection accuracy and false positive rate under different attack scenarios. In this slide, we present the comparison of our INDRA framework with the prior works. The figure on the left shows the accuracy of INDRA versus prior works for different attack scenarios. And the figure on the right shows the false positive rate of INDRA and comparison works under different attack scenarios. We can see that INDRA outperforms all prior works in detection accuracy and has the worst case false alarm rate less than 2.5%. In order to understand the overhead of our proposed INDRA framework, we implemented INDRA and the comparison work on an NVIDIA Jetson TX2 board. We conducted two different experiments. In the first experiment, we studied the memory footprint of INDRA and the comparison works. In the second experiment, we studied the average inference time of INDRA and the comparison works under two different configurations. In the first configuration, we used a single-core ARM Cortex-A57 CPU. And in the second configuration, we used a dual-core ARM Cortex-A57 CPU on the Jetson TX2 board. We noticed that INDRA achieved the second best performance in both experiments after RepNet. However, the results from the previous slide indicate that we're able to achieve higher detection accuracy and lower false positive rate than RepNet with a very minimal overhead. In order to evaluate the scalability of our proposed approach, we've considered 6 different system sizes as shown on the x-axis. The y-axis represents the average ECU utilization. We've considered a pessimistic estimate of 50% ECU utilization for real-time applications. This is shown as the dotted bars. The solid bars on top of the dotted bars represents the overhead cost by running the intrusion detection systems on the ECUs. It is important to have the ECU utilization below 100%, as exceeding it can cause undesired latencies, leading to missing deadlines. Thus, INDRA has a very minimal overhead that scales favorably to increasing system sizes. In conclusion, we propose INDRA framework that uses a GRU-based recurrent autoencoder model to learn the normal system behavior at design time and uses intrusion score metric to quantify the deviation from the normal behavior at runtime. We presented an analysis towards the selection of intrusion thresholds. We compared our INDRA framework with best known prior works in the area. We've also implemented our proposed intrusion detection system and the prior works on a real hardware and performed an extensive scalability analysis. In a nutshell, INDRA outperforms all comparison works in both detection accuracy and false alarm rate. Thank you for listening to my presentation. With that, I would like to open the floor for questions.